Let's continue with our overview of the important type classes in Haskell, and let's have a look at the show and the read classes in this video. So let's start with show. That's a class that you've all worked with in one way or the other already, because as I think I said before, the show class is what GHCi makes use of internally whenever it prints a result of the evaluation of an expression back to you. So you can see that the show class consists of three methods, and the primary one is called show, which takes something of an arbitrary type as long as it's an instance of this class into a string representation, so a textual representation of the value. And the convention is that the representation that is supposed to be produced by show is a developer-oriented representation of the value, so that typically the representation of a value looks like something you could have written as part of a Haskell source program. So obviously this desire to provide textual representations for things of various different types that also arises in other contexts, such as applications where you may want to present to your end user various different concepts in a textual form. You should probably not use the show class for something like this. It's best then to define a type class with a similar method that is specific to your particular application that provides these representations. As you can see, there is also a show list and a show sprec method. These are used internally to get the right textual, basically they're helper functions for the show function. They're used to get the right desired textual representation in the end. In particular, show sprec has something to do with the placement of parentheses and printed expressions, and show list has something to do with the rendering of lists. But as I said, they're essentially just helper functions. And the minimal definition here is show sprec or show, but you will rarely ever define an instance of this class on your own. You will use deriving as we already have in a number of places. And I'll present deriving in one of the next videos. So let's have a look at a number of examples. So we have already seen show in a number of contexts, but here there is an example of calling show on the Boolean false, and actually now there are two occurrences of show here in a way, but that are playing a role. But we are producing a string representation of the Boolean false, right? And then that string is kind of printed back to us by GHCi, and we can see that we get false surrounded by quotes. And if we do the same thing for a number, then we get a textual representation of the number. If we do show on a string, then we get a string representation of a string. So we get a string that contains the quotes in escaped form that surround the word hello. If we do a show of a character, we get this. But in general, this is as expected. Slightly more interesting if you start showing things of combined data types. So for example, if I show a pair of a Boolean and a list of numbers, then it still works, right? Or if I show the just of this, so basically a maybe of a pair, right? That also works. And also if I show the just of a just 3, and that also works. And you can see that here the show instance does have to be a little bit careful about the placement of parentheses. So that's why this shows prec is there. So sometimes expressions do need parentheses for proper grouping. If you would print just 3 without any parentheses, it would not be parsed correctly, right? And here in the pair example, the parentheses were coming from the pair, so there it was easier. But here you really have to look at the context in which a sub-expression appears. So if we look at the instances of the show class, we see that there are quite a few again. So actually very, very many types are showable. We have usual suspects, the integers, booleans, characters. The ordering type that we have seen before is also an instance of show. The list type, maybe, and then tuples. Right, that's all the extra stuff here again, and doubles and so on are also showable. Right, I'm basically, as with most other classes so far, the notable exception are functions. Functions are not showable. That is also, if we go back to the very beginning of the course, there is this situation that you're in GHCi. So GHCi uses this print function, which is defined in terms of the show function, to print its results. And if you start entering a function type into GHCi, you'll see that there is no show instance for functions, and you'll see a hint that GHCi is trying to call print on the result of what you've just evaluated. It is perhaps interesting to briefly demonstrate what happens if you define your own deviating show instance, that this is really what GHCi is doing. So if this was happening in a prelude context, so I hadn't any file loaded, but if we go back to our source file here, we have our choice data type here, and it is currently not an instance of show, I believe. I did not write deriving show. So if I load overloading.hs and I try to type in rock, I get that there is no show instance for choice. So that gives me the freedom to actually not derive an instance, but to define one myself. And one option I was given by the minimal pragma is to just define the show method. Remember that we have the instance signatures language extension enabled, so I can write a type signature for my specialized show function. So for the choice type, I have to give a definition here that goes from choice to string. I can just do this by pattern matching. And now I can just choose my own string representation. So I can in particular say I just want to have one lowercase letter, let's say, representing these rock, paper, and scissors. And then if I load this and I type rock now, I actually get, even from GHCi, even without explicitly calling the show function, right? And I get this representation R back. This is exactly because, as I said, the print function is being used. The print function is making use of the show functionality. So actually the implementation we are choosing is used to generate this representation. But as I also said before, this is not recommended. I mean, there are situations in which something like this may be useful, even from this viewpoint that the convention is that it should like give a programmatic developer-oriented representation, such as it could appear in a Haskell source file. But it is also an easy way to create a lot of confusion, right? If you do this. But nevertheless, it is being applied, and it also extends to to occurrences that appear inside other data structures then, right? So one more final remark on the show class before we move on is that this show list method, which you rarely ever need in practice, is being used to make sure that strings get a different representation from normal lists. So as we all know that strings are by default lists of characters, but even if I enter a list of characters like this, the show representation for strings, for lists of characters, is this list in double quotes. And you can observe that by calling show explicitly on such a list as well, you'll get the string representation, right? So that is what the show list method is being used for, to get a deviating representation for lists of one particular type. I think the only place where this is used in practice is the lists of characters instance. Okay, I think that's enough for the show class. So let's look at the read class next. Let's have a look at read. So again, there are many instances. Let's scroll up. So read is actually even more extreme. In show, we already saw that there are 3 methods, but only one of them is the method that we're typically using. The other 2 are essentially just helper functions. For read, the situation is that there are 4 methods in the class, and they're all helper methods. I mean, none of these are actually the ones that you're typically using. The function that you're typically using, or the functions that you're typically using, are defined in terms of these helper methods, and you're typically not defining your own instances of the read class either. And the one frequently used function is this read method, even though it is somewhat problematic, as we shall see in a moment. So this has a type that is dual to the type of show. So show goes from A to string, read goes from string to A, as long as A is in the read class. We have perhaps not explicitly talked so much yet about functions that are overloaded in their result type, even though we have already used such constructs. This is a little bit unusual in many other languages. Many languages support some form of overloading, but usually it's overloading that is depending on the argument type. Overloading on the result type is interesting because it's not the function argument that determines which instance of read we're using. It's the context in which the function is being used. So we've seen this with min-bound and max-bound before, where I said that if we just type in min-bound, it is of type A, and we have no contextual information at this point, right, as to how we want to use it. And one option to specify that is to give an explicit type annotation. That is something that we can do for read as well. If we want to call read on a string such as false, and say we want to recognize the string false as a value of type Boolean, we can give an explicit type annotation. That is one option. And then it successfully parses as the Boolean false. But another option is to just provide a context that makes it clear what we are expecting. And such a context can be another function call. So if you remember, the function not is of type bool to bool, so it expects a Boolean. So if we now use not on the result of read false, then it is clear to Haskell that we expect a Boolean here, and therefore that we want to use the bool instance of read, and that we want to try to parse the string as a Boolean. and it will successfully parse the string as a Boolean false and will return true. Similarly, if we try to parse the string 1, 2, 3 as an integer, that is fine. And if we provide a context in which it is clear that we're expecting an integer, then it is also fine. Similarly, if we say we want a list of numbers, and we use it in a context in which it is clear that we expect a list of numbers by appending it to another list of numbers, then it also works. Right? So if you have this overloading by context type, often you still don't need a type annotation. But you have to be clear that the context in which you use something determines what parser you use. So now let's look what happens if something fails, right? If we try to parse a list of numbers in a context where we expect a Boolean, or if we would give a Boolean annotation, then we get a crash. And that is why I think the read function, once again, is not desirable. I mean, maybe interesting for ad hoc experiments, such as what I've just done, or for something very quick and dirty. But in general, it is not something that should be used a lot in robust programs that you want to write, because it is very easy to provoke crashes, and the parser is not particularly forgiving either. Right? I think spaces and parentheses are about the only thing that this parser can deal with. If you say, read false was okay, right? But I think it is okay to put spaces in front and spaces in the end. That will make it work. And to put redundant pairs of parentheses in is also fine. But anything else, for example, turning the uppercase f into a lowercase f, is going to be wrong. Right? Or having, I don't know, a comma at the end. This is also going to be wrong. So it's very easy to get crashes. Right? The idea of read and show is, again, but that is just a convention, that in general something that has been produced by means of show, right, should be readable again by means of read. So that is something that you should in principle be able to rely on, at least. There is a better option if you don't want to use this partial function read, but you will have to go beyond the prelude. You'll have to import a module that is called text read, and that gives you a function that is called read maybe. And read maybe is still overloaded over the result type, but it produces a maybe result. Yes, and so that means that the context in which you use something is different, or if you provide a type annotation for it, you have to make be clear that you're in a maybe context now. So for example, if I want to parse false as a Boolean again now, and I want to give an explicit type annotation, I would have to say maybe bool here. If I say the call of read maybe to false is a bool, I'll get a type error, because that's not possible. We cannot give this expression the type bool, because read maybe always returns a maybe. So that means we have to explicitly say it's a maybe bool, and we get just false out. And then we can use our functions on maybe that continue dealing with it. But now if we say we want to parse this as a maybe int, then we get nothing rather than a crash, and we can deal with it. So this is much more robust. There is another issue that can arise in the context of working with overloaded functions, and that is that of ambiguity. And we have been seeing some forms of ambiguity in the sense that something is overloaded on the result type, and we don't have enough contextual information. And we again, this also arises in the context of calling read maybe. So if we don't give any kind of type annotation, then what happens? Then again, GHCi will default. GHCi will actually choose the instance for the unit type. And you can see that by putting in the unit value. This is the only thing that will succeed in such a situation. And if I actually enable all warnings in GHCi, I can do this with a GHCi command like this. You can even see this. You will be warned about defaulting, and it will tell you that it made this choice, that it picked the unit type for the result type of read maybe, essentially. There is still a little bit, the type error message is not easy to read because there is this printing of the result mixed up in it again, which also contributes to forcing. So you actually need to resolve a read constraint and a show constraint. Both of them are defaulted to unit, but that's okay, I guess. So that's what happens. That's something to keep in mind. But you can have even stranger situations in the sense that you can create things that are going through types that are no longer appearing in the result. So we can make a binding for something that takes an X, which is supposed to be a string, and then it reads the X, and then we show the X again. All right, so this uses the partial function read and then show again. So the type of this function, it looks to be string to string, and if we ask for the type, this is a warning again, and I'll go back to that warning. If we ask for that type, it is actually string to string, right? But if we look closely, read delivers a type A, that is a member of the read class, and show consumes a type A, that is a member of the show class. And we don't specify anywhere what this type is. So this is an intermediate type again, and there is no trace of it on the outside because we go from string to string. So there is no way on the outside now to specify which type we want. So that means that there is some sort of ambiguity on the inside. And again, if we do this in a GHCi context, we get defaulting of the intermediate type to unit. But I think it's important to say that GHCi is more eager to default in general than GHC is. And if we do the same thing in our module here, if I define string x is show of read of x, you'll see that, okay, I get the string to string inferred here, but at the same time, this is underlined in red. And you see that I'm getting an error message that says that there is an ambiguous type variable arising from a use of show. And this is what GHC does if it does not default. GHCi typically tries to default everything to the unit type. That is the general principle, which often leads to confusing results as well. But in an interactive context, the idea is you want to be able to try out as much as possible. In a non-interactive context, the idea is it is better to be explicit about what you want, and so defaulting is applied less, and in some situations you'll just get an error message about if there is an ambiguity and the contextual information is not sufficient to make the right choice or to make a choice about how to resolve a type variable, you get an error message. And the hint to look for is always if it mentions an ambiguous type variable, right, then it is typically meaning that you have some overloaded functions that you're using and there is not sufficient contextual information available to resolve this type. And then if you haven't made another mistake that leads to this, then the typical solution is to provide a type annotation at the right position. So remember, in order to resolve this is a contrived example anyway, but in order to resolve this, we have to annotate the intermediate type here, not the outer type, because the outer type is string, we know this, but the result of read, we would have to say something like the result of read should be an int. And now it's clear we want to parse the string as an int and then show the int again. And now the error message goes away and the type of strange is just string to string. And why do I still get top level binding? Did I not say it? Oh, okay. Now I'm just getting another error message about defined but not used. About this y. Let's get rid of this warning as well. Okay, so now this loads without errors and warnings, and now I can observe that strange works if I use it on a string that represents an integer, because then parsing it as an integer and showing it again will just lead to the same string. But if I use this on anything else, it will crash. So this is as I said, this is a contrived example. You should probably not use read anyway. But as soon as you're working more with overloaded functions and you're combining them in various ways, you may occasionally end up in such a situation that there is an intermediate type somewhere where the contextual information is not sufficient to uniquely resolve its type. And then you may get an error message involving ambiguity, and then providing an explicit type annotation is the right fix. Otherwise, read maybe is the function to use if you really want to parse things. It is a useful function in a situation where you, for example, want to parse something as an integer. You get some user input, and you want to parse it as an integer. That is a good use case for read maybe, right? Or similarly, if you actually want to parse something as a Boolean, perhaps. Although I think there it's already strange. You would probably not use false or true in the Haskell representation as an actual representation, but as other number types, perhaps as a floating point number. If you want to parse something as a floating point number, then the read function may still be useful. Okay, I think that settles this. And I think in the next video I'm going to present to you how to use deriving. We have already been seeing deriving before, but I think it's time to revisit that.